Hello and welcome to the Code Unboxed series by TrustInSoft. As we had mentioned before, we'll be analyzing Trampoline OSEK today. With me, I have Roland, who I'll introduce in a few minutes. Before we do get started, though, what I want to do is just some housekeeping items and run through our vulnerability disclosure policy as well. This is obviously being recorded. We will open it up to questions at the end of the presentation and of the analysis as well. And we will be sharing the on-demand version as well at a later date. So if you're watching this live now, great, you can jump in for any questions. And if not, feel free to watch the recording at a later date. We do have a vulnerability disclosure policy that we follow. And what that is we do a 90-day disclosure or notice about any bugs or vulnerabilities that we've identified that we'll be talking about today. We do a 30-day reminder as well. And as always, any code that we're analyzing, we're not going to show vulnerabilities during this Code Unboxed session that a owner or a representative of the respective code has not had the opportunity to either fix or not. So we do follow the standard vulnerability disclosure policy. With that, as I'd mentioned, Roland is Roland. Welcome, and thank you for putting together all of the analysis that you've done. Do you want to just give a little bit of background of yourself?
Yeah, so Roland Dudemain, I'm the Director of Field Engineering, pre-sales, and also analyst team who are actually using the tools for the account of our customers. I've been working on RTOSes for more than 20 years and hypervisors for various companies. I've been contributing a few pieces to the open source world as well. If you search my name, you'll find it. And I've always been passionate about making high quality software, whether that's especially for critical software, so safety and security. We can have good discussions if we ever meet someday.
Thank you. So before I hand over the analysis to Roland, I just wanted to run through what we'll be going through today. So if you're not familiar with Trampoline OSEK, it's an open source real-time operating system specifically designed for small embedded systems. It does adhere to the OSEK and VDX standards for interoperability and offers predictable performance due to its static nature. So it's pretty well suited for various real-time embedded systems and applications. Think about like industrial automation or IoT, medical devices, automotive applications, such as control systems in self-driving cars or even engine management units. And that's what Roland will be sharing some of the analysis that he's done and be running through the analysis. A little bit about TrustInSoft if you're not aware who we are. So our mission as a company is really to empower developers to deliver mathematically proven zero defect products. Oftentimes when we mention that, people go, well, what exactly does that mean? Our tooling that we have, we use abstract interpretation and formal methods to really deliver in three areas, right? One is from a depth perspective where we ensure that we're identifying 100% of the flaws and vulnerabilities, and that's a tall order to mention. The reason we can state that is just based on, as I touched on earlier, the abstract interpretation and the formal methods that we're utilizing within our solution. The other is still based off those same principles as well. We're able in a very short time and with very little effort to provide exhaustive analysis. So instead of writing thousands of unit tests and that just with some generalization inputs, we can actually perform billions of those respective tests just from one generalized test input, as I mentioned. And then, of course, there's the formal methods side of the house, and that's the mathematical proof that if we specify and state from our testing that there are no critical undefined behaviors or no critical bugs from the testing. We have that mathematical proof, i.e. formal methods, that it's guaranteed that there is no critical runtime errors. So what does that mean in the real world? When you're comparing or looking at a typical static analysis, oftentimes that typical static analysis misses specific code paths, right? And as you can see, just some 3 typical examples as well that I'm sure most listening and watching live here would be aware of. If you're not, Heartbleed was a very well-known OpenSSL bug, which was the result of improper input validation. More recently, with the CrowdStrike outages, that was a result of invalid memory read. And then maybe a little bit older, one of not so much the most expensive bugs anymore in the world, but it resulted in a rocket explosion, was the Ariane flight, and that was the result of an integer overflow. So using something like TrustInSoft with abstract interpretation, you're able to really analyze and inspect all of the respective code paths for and ultimately reduce the number of false positives that you're getting, as well as have that mathematical proof. So with that, I'm going to hand over to Roland now to spend and do a really deep dive in the analysis that he's done. So Roland.
Yeah, so like Gavin briefly explained earlier, Trampoline is a real-time. What we wanted to look at in the second session was to look at some automotive software. And open source automotive software is not, it does not exist so much. So that's where Trampoline actually is an interesting example of that. And so the intention of that session is to not judge what's there, but just take whatever is in the source and see if we can find issues just using it and lightly like that. So let's start to look at the code. The first step to analyze the Trampoline RTOS is to gather the sources and its dependencies. You can go to the repository for GitHub and then first download the sources by doing a clone of the software. While this is ongoing, we can scroll down. There are multiple targets there. We will choose this one, the STM32F3, just because. And reading further, it seems like there are 2 dependencies. One is the G-oil tool, which is part of the sources, but we can download the already prepared binary to simplify. And and the ARM toolchain, which I will download separately. And I have a link directly to the correct location. This is it for this one. We can also go to the example of this platform to see where we can run the instructions. We can see the initial instructions here, and we will run through them once we have the project open. I first need to install the G-oil tool and the ARM toolchain. So to not mess with the installation, I will create first a TrustInSoft project and set them up inside. I like to disable the extra message in the tool. And now that we have the base framework, I can create directories for the ARM toolchain and the G-oil tool and extract everything. I can then place those directories in the path. and add this directory. Sorry, arm tool chain, and path here, and /bin. Now I have access to the tool. We can now try to build the tool, to build the software. So let's go to the directory of the example, and now run the goil tool to generate some files. And normally the command is make.py, but I will use bear to be able to gather the compile commands. Compilation succeeded, and now we have a compile commands here. Go ahead and look into it, and we have several files. Now let's try to insert everything into the TrustInSoft configuration. So let me open the config.json and do some cleanup, because there are many commands that are not helping with readability, but are good for newcomers. I will keep this line because that's adding the compilation database, and we can add it here. That's the path to our example here. And okay, then the architecture is going to be ARM EABI, probably GCC ARM EABI, because I expect some GNU extensions. And I'll get rid of that initial parsing analysis because we will get directly into the core of the behavior and then get rid of the last one. Okay, now we can add the original file. And well, let's see. Do we start immediately with all the files? So a quick way to do that is to grep through the compile commands and find all the files that were used. Grep file commands. Now we have the complete list of all the source files that were used in the project. That will be then the basis for our analysis. I'm going to leave the stubs in case we need to add some, and just remove this. We also need to remove the assembly files because the analyzer focuses on the C and C++ language. And there's one more here. And if everything goes well, we should be able to start the first analysis already. Oh yeah, let me put it in verbose mode. Normally the output is pretty quiet, but here we want everything. Okay, I left an assembly file. Where is it? Here. Oh, I left two actually. Drag in. Did I miss another one? Oh yeah, I missed that one. Okay, so what's going on here? So, well, it seems like we've reached the end of the step of the parsing. So let's focus now on trying to figure out what's going wrong here. The first thing that we can do is to run the inspector to see the problem live in the root cause investigation interface. This will open a web browser. Okay, here. And now we can look at what's going on. So we have two potential UPs, but one of them is an incorrect access at this address. If I click on port, I see that this address is a hexadecimal address that seems to be, if I read the code, a GPIO address. So yes, it's an STM32, so it's a small chip with registers that are available in memory, but right now there's nothing available in memory or declared in any way in the system, and so this address does not exist because the symbols are at an arbitrary address in the analyzer, abstract address, and not a specific address. So what we need to do is to describe that there is a GPIO type def available at this address. So let's see and go in the source to do that. Well, actually, let's first look at that GPIO type def. Seems to be described in the header here. So we'll go into this one. And well, that's great. We have all the device registers described here. Let's see, do we have another one? So let's scroll. And can we find that address? It was 40,400,000 something. And so that would be this one. So now we need to describe to the system, to the analyzer, that there is actually a valid address of type GPIO type def at this address. The way we can do that is to describe a new variable that will use a special attribute called thisaddress. And to be able to do that, we can first include the header name, which is, I forgot the name, of course, this copy relative path. And of course, we want to remove this path. And then to describe that GPIO type def, we'll create a new variable, and let's create it for all the GPIOs at once. So this address, and then give it the GPIO A base. Obviously, VS Code actually does seem to understand where it's defined and knows about GPIO base. And let's see if we can duplicate that. No, like that. If we look in that header, we see that there's A, B, C, D, F, no E, but okay. So let's do B, C, E, F, E, F. Okay, so this header is not going to be understood and reachable by this C file because this file is a new file that we created. However, we can describe that this stub.c should be analyzed, should have the same compilation options as another file that we know. And so there's an option for that, which is cpp compile like. And we can give a dictionary like this. And so I'm going to take the original file. And well, it's considered it's going to be in the same as the startup file, which seems to have a lot of definitions. And that would make sense. Okay. Let me kill this and try to run to see if we actually had something better. At least the parsing succeeded, so I did something good. Okay, still two alarms. Well, let's inspect again. And now if we look at here, we see that we went through that port. Well, let's click on the undefined behavior. Seems like now we have a different kind. It's no longer GPIO type def, but it's RCC type def. So I guess we need to describe the RCC type now. And probably we'll have to do it again for a number of of elements. So let's see if we find RCC somewhere. RCC base is here. Okay, well, there you go. And but this is quite an iterative process. We can try to do it again and again and again. I think I'll save you some time and do it once more, and come back in a few minutes after I've done it for all of the missing registers. Okay, now we have one undefined behavior, another kind, cystic. Okay, well, yeah, clearly it needs to have a little round to add all of them. So let me add all of them now and come back after that. So I can add all the necessary memory ranges to solve all the memory declaration that are necessary to do the analysis. Once that's done, I can restart the processing and open the inspector on the code, and hopefully we will not have anymore any undefined behavior, which is the case. That's good news. But now we have a missing function. That missing function seems to be TPL start OS. And so that means the code calls that function, but we don't have a body for it. So there's no way that the analysis can continue. So let's go back to the source. It is probably a missing stub. And if we go to TPL start OS, we can here see that this is an assembly function. That assembly function is doing a system call, software interrupt. So in ARM, this is system call, and it is calling that with the argument start OS. That argument start OS, if we look at the source of it, is the index 1. And if we go back to that TPL start OS, we see that there's actually another service function that probably corresponds to the other side of the interpretation, referenced in a dispatch table, and this is also index 1. So that's fine. We now can have the function that will use the dispatch table and implement also an equivalent to that. That function that calls the dispatch table seems to be doing some boundary checking with syscall count, and then computes a particular offset into that table, and then does a bxr3, which means assembly branch to that function, branch to that pointer. Okay, so now we have to do an equivalent in C code. So let's do that. So there's first that start OS function, which is not taking any argument, and we can make an implementation. Let's see, this call function in assembly calling that dispatch table is called PPL primary syscall handler. So let's do that, and we'll make it call it with that OS service ID function argument, because we want that function to be reusable. Is there a public prototype for that primary syscall handler? Let's see. There seems to be one, but well, we know that there's an argument, and it seems like this function is not completely compatible with one of the source declarations. So it will take a uint32t because that's what it could be in a register in 32-bit ARM, and then we'll use the dispatch table with the offset call ID, with the array index call ID, and then call the function. So now we need to add some declarations. So dispatch table is described somewhere. Actually, I could just control-click on it, and we see that there's a declaration and also a declaration of the underlying type here. So we can just do this. We're also missing some declarations. Syscall count is described somewhere in a header, so we need to include that header here. TPL service IDs. And that seems to be enough. So let's do the inspection again. And interestingly, we have a different implementation of TPL Start OS. Okay, so fair enough. Let's go to that declaration. Okay, the declaration is a little bit different. So let's see. So now we have more declarations to include OS code. Okay, too many OS codes. So we need TPL compiler.h. Include TPL compiler.h. We also need that app mode type. App mode type is inside TPL OS. So let's include TPL OS. TPL OS. And see if we get anywhere with that. Oh yeah, okay. So semicolon, silly syntax error. All right, well, it seems like the analysis has started, so let's go look at that. And now the analyzer is parsing, and there's one undefined behavior for calling TPL start OS service. So we did the chain right, at least. And it tells us that the pointer type that we actually use is void, but it was finding in the table an incompatible pointer type. Of course, start OS service takes an argument, and that's what we saw originally. But okay, so let's go back. And that seems like we have a bigger problem at hand, because if we go look at the dispatch table, that dispatch table, let's see, how do I, let's see, I reached it by looking at service ID, TPL start OS. But that's strange, because when I look at this here, that means that we have some functions here that take a void and return a TPL application mode, some function that take a mode and return void, some function taking an error and returning void, and so on. This is a void. So we have actually a table that's a mixture of many different function pointers with many different prototypes, but that's obviously not allowed in the C standard. So there's obviously something going on with the some magic going on with the assembly. So now we need to create some more advanced code that will not just try to generically call the function with no argument at all, because this is necessary. It is necessary to pass relevant arguments. All right, so again, this is something where we could try to make something truly equivalent to the assembly code, but in C language, this is impossible to mix pointer types. Instead, what we're going to do is to try to emulate each call in a very detailed way. Because this is going to take a long time, I prepared it, and what we're going to do is to just import a particular function file that I prepared and copy it into our stubs here. So what happens is we have our start OS function that calls into a specific advanced handler here. And that advanced function handler is creating a very manual call to each of the possible functions that were called in the dispatcher, but with the correct prototype called. So our function start OS service here is taking an argument mode, and that argument mode is now a generalized version. So instead of a fixed value that was provided as input, it is also doing a robust generalized approach and verification by taking all the possible modes that the the system may enter. And likewise for every other argument of every other system call, which is great because we're doing a very large robustness call into the OS, which could be good for security. All right, so let's continue that particular, try that particular analysis. I'm going to go back to the terminal and try to inspect it one last time in the interactive mode. And let's see if it gives better or worse results. But at least we know now that we can call all the system calls of the platform, and hopefully we will find interesting things. So all the files sparse, but we have 5 undefined behaviors reported. So that's too many, or at least we don't want to look at that in the inspector. Let's look at that in the report. And that will probably be the end of our demonstration. So I'm going to just run it again in the command line mode. And the analysis time is short enough that I can just do it like that. And then let's open the report. That report shows again our 5 undefined behaviors. And if we look at the alarms, we see now these 5 errors. So let's look at least, it seems like they are located in only 2 locations, that serial putchar function and init.os. In the putchar function, we see that it tells us that it's an overflow of that particular value, and yeah, well, that seems genuine. The txbuff head is indeed could overflow here, and there is a wraparound to a modulo to limit it. And that serial txbuff head should be below that function. Actually, since it's const int, I expect that serial txbuff head is also a signed integer, and signed integers are real problems and they're undefined behavior. Well, okay, let's look at the other ones. So this is quite similar. We see that it's here the same 2 to 3 lines later. That same overhead, that same overflow could lead to an access to a particular serial buffer, and it's not using next, but it's really using the original value. So that could actually go totally out of bounds. And especially now we have the confirmation that txbuff head could be negative. And if it's negative, then that's a big problem. Let's see, it's third out of bound, but on the same line. So we have a problem with the serial putchar in the terms of boundary checking. Maybe the solution would be to make it unsigned, and that would solve a big category of problems. Another one, TPL init.os. Let's look at that. Here we see that the error is that app mode that is passed as an argument during the execution should be below 32, so 0 to 31. But it seems like it's taking the mode in a way that could be that would be either negative mode, because that mode apparently is a signed char, and up to positive mode. So either it's negative from -128 to -1, or it's positive above 32 until the maximum, and those are invalid values. It seems like it's missing boundary checking again for that value. And if we look at the last issue, well, it's kind of the same problem. If the app mode is shifted, then the mask will be shifted, and it's also expected to be a problem. Also, if the value is 31, so probably 0 to 30 should be the correct value. So there, anyway, there's a boundary checking issue with app mode. So this is the end of that demo here, and we'll switch back to the slides. So in the end, we found a few interesting things. So that was good. Then we found a portability issue with a missing header. We found a much bigger design issue with pointer types and the table with multiple arrays. That caused an interesting longer than I wanted stub writing. And then we found a few issues in the serial driver, which is then specific to the configuration we chose, and then something more generic with a potential issue if the code is misused, if the API is misused, where it would lead to a crash. So that's good for half an hour of investigation there. So this is the end of the presentation. So what's interesting here is that, again, we could see, we could do a nice tour of how the analyzer can be used with the command line interface, the use as you would deploy it in a CI with the reporting, the interactive investigation interface, looking at the source code. Looking at the code coverage is something that's available in the report as well. And from a methodology perspective, this is something that could be expanded to do a more systematic verification of the software. But most of all, we had fun. We had fun for half an hour.
Yeah. Thanks, Roland. I think something's up with your video because it keeps flickering back on and off. But anyway, I think overall, great, awesome overview and analysis of Trampoline. We will, as I mentioned, this will be available via recording. Just as some final steps, if you do have some code that you would like analyzed by TrustInSoft, by all means, feel free to reach out to us on any one of those channels, either email, LinkedIn, or go to our website, and we'd be happy to have you join or even participate in our next Code Unboxed. Our next Code Unboxed will be in about 2 months. We run these every 2 months. Or alternatively, reach out to find out more about the TrustInSoft Analyzer. Thank you for joining today. Goodbye.
Thank you.